Okay, so let's continue. Now I'm going to use the other three videos to talk about numbers, okay, or to talk about how may we calculate some numbers from the original data set to summarize that data set. The first thing I want to talk about is about central tendency. So in general, we may sometimes use graphs, but sometimes we really need the help with numbers. Okay, just like you all have this experience. When you get a set of data, you first calculate, for example, its average to get an idea about, in average, how's the performance of a salesperson, or what's the yield rate of a manufacturer, something like that. Okay, so we need some numbers to summarize a data, that's for sure. So that's our plan for the next three videos. These numbers may either the parameters for populations or statistics for samples. If you can get the whole population data, you can calculate those parameters directly through the formulas we are going to give you later. Or if you only have samples, you may also use formulas to calculate statistics. For all the concepts or terminologies or measurements that we're going to share with you, we have a version for parameter and another version for statistics. Okay? Sometimes the formula will be the same, sometimes will be different. We're going to see that. In this video, I will talk about central tendency, about how the center or how the middle part of this data set look like. Okay, that's central tendency, or somewhat we say where is the data, or where are the data. And then we want to talk about variability. It's about how this data spread out the whole spectrum. The last topic will be about correlation among two variables. Okay, here let's look at central tendency first. First, let's look at this example. Suppose we have a baseball team, and in this baseball team, there are 20 players. We record their players' heights in centimeters as these 20 numbers. Before we do anything, again, we would like to draw a histogram to get some ideas. Okay, so the data ranges from 160 to 180 whatever, okay, 86 or 89. And then we can see most people are of this height, somewhat reasonable. Okay, so that's about graphs. Let's stop it. Let's try to describe the central tendency of this set of data. The first thing to measure central tendency is the middle point. Okay, what's the middle point of this data? Or what's the guy who is higher than one half of the players and shorter than the other one half players, right? Who is the guy who is the 10th highest player? That's the middle point of this data. Let's try to look at it. That's one thing. Also, we want to know among all these heights, which number is the most common? That's the first idea we want to introduce here. That's modes. Okay, the modes is or are the most frequently occurring values in a set of data. In the previous example, we may count. Okay, there is one guy whose height is 162 centimeters. The other guy 165, and so on and so on. Oh, for 172 there are two guys. 175 there are three guys, and so on and so on. After this, we can say that the modes of these 20 numbers are 175 and 178 because these two numbers are of the highest frequency. Here, we do not group the data. Okay, these are the original data, ungrouped data, and then we calculate each value for its frequency because some values may be repeating each other. Okay, so for 175 and 178, we have 3 for each. these are the highest frequency data points, and that's the mode of this data graph. Of this data. In general, it's actually better to look at qualitative data when we are calculating modes. Okay. Otherwise, if we are not so lucky, it's possible that once after we calculate several heights or several weights or several income levels, whatever, there is no mode at all, right? For example, if I have only 5 players in a basketball team, it's highly likely that no one is of the same height. Then there's no mode, or you can say everyone is the mode. Then that's useless. Okay, so for qualitative data, we shouldn't have that issue. Okay, so that's better. Now, the number of modes actually means a lot when we do statistics. The data of that team, actually that's the team that I am participating in because I'm in the department. So that particular team is, we say it is bimodal. That means there are 2 modes. In general, we may have unimodal data if there is only 1 mode, or multimodal if there are more than 2. Okay. Sometimes when we say bimodal, it's actually meaning that there is 1 unique mode and another number whose frequency is also quite dominating. Okay, like this graph. In this case, we say this is indeed the mode, but this particular value is of a high frequency that is much higher than numbers around it. So in this case, we also say this is a bimodal data set. Okay, so this is unimodal. This is also unimodal. An important type of unimodal data is the bell-shaped data. Is this one, okay? Because it somewhat looks like a bell, right? We don't want to talk about details about bell shape in this lecture, but in 2 or 3 weeks, we will talk about something that is highly related with bell-shaped data. We're going to show you that when a data set is of bell shape, there are many good properties. But anyway, let's skip it now. So that's mode. That's going to count for the most frequently occurring values. And now let's look at the middle value. The median is the middle value in an ordered set of numbers. Or roughly speaking, we are asking what is the number that is above half of the data and also below half of the data. That means it's at the center. Okay, so there is a formula. Let me briefly explain it. Suppose we have n numbers. If we have an odd number, then the median is understandable. It's just the center point or the middle point. Okay, if we have 1, 2, 3, 4, 5 values ordered from left to right, then the middle one should be this one. Okay, not a big deal. But if we have an even number, okay, like this, then the middle point should be somewhere here. Okay, and then our formula is going to ask us to find this number and this number and do an average. So for example, if we are looking at these 7 numbers, then the median is 5 because 5 is located exactly at the middle, right? It's smaller than half of the data and bigger than half of the data. But if we have 6 numbers, then the median would be the average of the 2 middle data point, and in this case it's 4.5. Formula is not so important because eventually we will use computer software to calculate this median, whatever. But I hope you understand the concept. There is a difference between odd and even numbers. We need to give precise definitions for them. Okay, one property of median is that it is not affected by the magnitude of extreme values, like here. This data the median is 5. But even if 9 becomes 900, the median is still 5 because we only care about orders. Okay? So that's why medians can not only be applied to quantitative data, it may also be applied to ordinal data. Okay? So it's more somewhat is more applicable. But the bad thing also happens here. The median also use part of the information. Okay? Here you have 7 numbers. They have their values, but you only care about their ranks, okay, their orders. So you are not caring about their values at all. And sometimes that may be a bad idea. So in this case, we say we only use part of the information, and that somehow motivates us to design or to invent the concept of average or mean. Okay, the mean or the average is just the average of all the data. Okay, like here, if we have a set of data, then the mean is to add all of them and then divide it by the number of data points. In this example, we get 5. Okay, so that's the way to calculate the average or the mean. One thing to keep in mind is that when you want to add some things together, they must be quantitative. You cannot add ordinal data together. That's not allowed, okay? Because it's just meaningless. In this case, all the information are used are used to calculate the mean of a set of data. So somewhat that's a good idea. But again, there is a bad thing. The mean is going to be affected by extreme values like this. The mean of this data set would be very much larger than the original mean is 5. Okay? If the data is really look like this, then of course there's no problem because the mean is just like that. But sometimes when we are keying data, for example, we probably made a typo and mistakenly put 20 after the last number, and that's going to give us a wrong result. But if we are using median, then that's not going to happen, even though we are lucky, just lucky. So in general, we need to be careful about extreme points when we are talking about means, and that's why outliers are extremely an issue when we are calculating mean rather than medians. Okay, so that's something to keep in mind. So mean and median, they are somewhat complementary. Many people use both when they want to describe a data set. Okay, now is something that may be a little bit challenging. We are going to tell you about population mean and sample means. So what are them? Suppose I have a set of data. This notation is an abbreviation of x1, x2, up to xn. Okay. When we have this set of data, we include everyone into this particular set notation. Okay. So in the future, you can see when we see this, it's going to be a set of data. Here we use capital N to be the population size. And then the population mean can be calculated like this. As the numerator is a summation from x1 to xn. Okay, so as we mentioned in the previous lecture, this sigma notation is to sum up all the numbers from 1 to n, x1 to xn. And after this summation, we can divide the summation by the number of data points. That's going to give us the population mean. In statistics, we use the Greek letter mu to denote population means, always. If this is just a simple data set, okay, we use small n to describe the sample size. In this case, the formula looks very similar, except that first we use small n instead of capital N to denote the sample size. And also we use x bar instead of mu to say this is a sample mean. Mu and x bar, they will be used throughout this semester as the notation for population mean and the sample mean. Immediately, you may have a question. These two formula looks just identical, right? The only difference is capital N and the small n, but they are just variables or they are just notations, right? So what's the point of defining two different formula or two different notations? So regarding calculation, indeed they are the same, but for statistical inference there is a huge difference. Okay, let me try to give you some intuition now, and we will spend a lot of time to talk about inference in the future. So the thing is that for population, if we can collect all the information about the population, we can calculate that population mean. The population mean is there, is fixed, it's just unknown to us. Okay, like the example we mentioned in the previous lecture. What's the average height of all the NTU students? Okay, NTU students is well defined. If you have a student ID, then you are NTU students. And then the mu or the population mean is there. There must be such that number. It's just that we don't know. And then we do a random sample to get a sample whose size is small n. Okay, maybe 100 and maybe 200 students, and then we do an average to get the average height or the sample mean. The sample mean is actually random. What does that mean? If today we do a sample, we're going to get 200 people and one sample mean. Tomorrow we do another survey, we're going to get another 200 people and another sample mean. Today, tomorrow, the day after tomorrow, we will get different values. And before we do that survey, we don't know what's going to happen. That's why we say X bar is random. And eventually, the only thing we may do is to use sample to infer the population, right? We use random things to guess the fixed number. That's what we do in inferential statistics. And that's where we need to apply probability. Okay, unfortunately, we need to apply probability because we need to understand how random this X bar is so that we can guarantee the performance of our guess. Okay, let's go to details in the future. The last thing, and the last two terms I want you to know is quartiles and percentiles. Intuitively, that's what you are thinking about. The median is at the middle. How about the first quartile? The first quartile is at the middle of the first half. That means it's at the 1/4 position. And the third quartile is at the the middle of the second half. So if this is the whole data set, this is median, and this is the first quartile, and this is your third quartile. Okay, that's the idea. And then we also have percentiles. It's just to divide the whole data set to 100 equal size dense intervals. And then for the p's quartile, that means p over 100 of those values are below it. Like for example, if we are talking about the 10th quartile, then it's probably here. The 20th is probably here. And then immediately you know the first quartile is the 25th percentile. The median is actually the 50th percentile, and this is 75. I will stop talking about quartiles and percentiles here, and also I guess we will not use them frequently in this semester. They are useful when you want to describe your data, but for inferences they are not so useful, and that's why I will stop here. You may need to know the concept, but for inference we just don't use them. Okay, so thank you.